This is a harmonic series, and you can notice that, it likely will converge, right? You can write the first couple of terms out, and you see it's 1 plus 1 half plus 1 third plus 1 fourth, and you notice that each term is getting smaller and smaller, so the assumption is that it might converge to some value. We can take this further by looking at the graph of a function, 1 over x, same thing as 1 over n in the x world, and we see that as the x values are going to infinity, there is a horizontal asymptote bounding the y values, particularly at 0. So does the series converge? Certainly looks like it should converge. There's a horizontal asymptote. It's bounded below. We can take the integral test to solve this problem, and we notice that the series in fact does diverge because the integral will result in a natural log term at infinity. Suppose we have a series a sub n and b sub n, where a sub n is bounded between 0 and b sub n. Well, we can use the direct comparison test to see if a sub n converges. If b sub n converges, then a sub n should also converge because a sub n is less than b sub n. And we can take a look at that again here for the same case. If we have, once again, a sub n is between 0 and b sub n, then if b sub n converges, then a sub n converges. But at the same time, if a sub n diverges, well then b sub n must also diverge because a sub n is smaller than b sub n. Now, does this series converge or diverge? We're going to use the direct comparison test that we just talked about to find out. Let's completely ignore the plus 1 and the plus 4 terms and simplify this approximately to n over n squared, and we can simplify that to even 1 over n. And we know that 1 over n is a harmonic series that diverges. So because 1 over n is less than our original problem, the series itself must also diverge because 1 over n diverges.